Oh, it's been so long since I managed to get to this unit. COVID and strikes and various other things. I think 4 years ago, I think we had a massive snow issue or something. We missed 4 or 5 days. I can't remember, but I just did not get to it. And magnets are just so much fun to play with. Let's talk about magnetic fields. I'm going to talk about right-hand rules. First of all, magnets are not di-charged, not two-charged. We call them poles. They're dipolar. What do we call them? No, positive and negative for charges. You know this without realizing it because you know compasses. North pole and south pole. So if this is a bar magnet, if that side was the north, then that side would be the south. Oh, and Taryn, like poles, repel. Unlike poles, attract. So you're already starting to see why I said magnetism and electricity, they're two sides of the same coin. They're going to behave somewhat similarly, but there's going to be one very key difference. Unlike electric charges, it's impossible to completely isolate a north pole or a south pole. Can't be done as far as we know. There is a smallest negative charge, it's the electron. There is a smallest positive charge, it's the proton. But if I were to break this magnet in half right there, all that would happen is that would become a south pole and that would become a north pole, and I would have two smaller magnets. There is no way to isolate a pole. In the same way that charges have action at a distance, but we said that was impossible. So our explanation was charges send out an invisible electric field like the tentacles of an octopus in all directions. Magnets send out magnetic fields like the invisible tentacles of an octopus in all directions. That's how we can say that a magnet can influence something that it's not touching. It is touching it. It's just touching it with something that you can't see, Paige, but it's there. It's a magnetic field. And in the same way for electric field, we had to define the direction. Gravitational field, we didn't, because stuff always falls down toward the center. Electric field, like charges, and so we had to define what was the direction of electric field. It was which way a positive would want to move if it could. We're going to have to define a direction, and here's what we decided. What's the direction? From north to south. Or, in terms of a compass, the kind that you navigate with, the direction a compass needle points. A compass points south. What, Mr. Dewick? Yeah, a compass points south. Mr. Dewick, I'm sorry, I don't mean to argue with you, but I've looked at compasses and the needle points north. No, it does not. A compass points to magnetic south. Mr. Dewick, I don't want to really be a kind of a pain here, but Mr. Dewick, I've done some navigating, and when they looked at that compass with me, they told me that compass was pointing north. There's a problem coming in our future. What's the symbol for magnetic field? Well, M is taken for mass, and uppercase M means something different. F is taken, uppercase F force, lowercase f frequency. And so we use, I think it's from a Latin word, capital B. And it is a vector, so I'll put the symbol on there. You'll often just hear me abbreviate. I'll talk about a B field instead of a magnetic field. Does anybody know the units for magnetic field? If you were clever, you'd look down 2 lines and figure it out. It's a popular car company now. Tesla's. Symbol, capital T. There's actually 2 ways to measure magnetic field. You can measure them in Teslas, or you can measure them in Gauss. You're sort of measuring the same thing, but technically measuring a little bit different. We will be using Teslas. The Earth's magnetic field is around 50 microteslas. So 50 times 10 to the negative 6. A very, very large magnetic field is 1 Tesla. Put your pencils down, look up. This is from a hospital somewhere that shall remain nameless. Late at night, some people are having a bit of fun with a multi-million-dollar MRI machine. What does the M in MRI stand for? Magnetic. And an MRI machine has anywhere from 2 to 5 Teslas. Here is a 4 Tesla MRI machine. No, not my video. Because you'll see this would not be happy if they got caught.
Whoa! So the force we're reading on that guy right now, just at that part of the magnet, is close to 300, 280?
About 300 pounds.
Let's see what we can get.
And it's holding a wrench suspended in midair, pulling it in.
Okay.
See it? Just floating there. Now, it's not quite dead center, and you'll see it slowly, all of a sudden it's going to get attracted to one side.
Any second, it's going to start dropping here. Just do it up.
There it goes.
Oh, that's all.
And now, it is giving us a reading of 500 pounds.
500 pounds. Hey, what will this do to a metal office chair? Let's find out.
This chair. No, let's try it out. You just tell that's about it.
Not that much metal in that chair, but enough.
About 60. We are at 700.
It's a menacing sound. Yeah.
700 pounds.
Oh, it's
Oh! And we have jumped to 1,300.
that's exactly really.
Yeah, jumped.
My stuff is right here, still on top of the chair.
Whoa.
So we're just about to hit the sweet spot.
Oh,
Baby!
There we go.
Okay, now. 1,700.
We are at 1,700, which is far more than this thing.
You just relax a little bit? Yeah. Okay, so it's...
Oh.
1,800.
1,800.
It's past the
No, there we go.
If you ever do go for an MRI machine, the people in charge will tell you to remove any metal from your body. There are always occasionally stories of people who have piercings they are embarrassed about. Those piercings are coming out. So you better tell them ahead of time, and you better remove them ahead of time. Otherwise, the machine will remove them for you. Okay. There are 2 main types of magnets. There are permanent magnets, like those 2 bar magnets that I brought out. Those are made out of ferromagnetic materials. But even better, there are electromagnets. These are magnets that are caused by an electric current. These are really useful because this gives us a magnet that we can turn on and off whenever we want to. What do the magnetic field lines look like around a single magnet? Well, first of all, magnetic field lines point from what to what? North to south. So if I follow a line, it starts out going north, points to the south. Okay? So as you can see, they all point from north to south. This is also the direction a compass would point. If you put a compass, for example, right here, the compass needle would point that way. If you put a compass right here, the compass needle would point that way. A compass needle points to magnetic south, not north. The Earth, magnetic field lines have no beginning and no ending. You can't isolate them, unlike electric field lines, which started on a positive or started on a negative. Magnetic field lines, through this, they would continue going and come out the other end. The Earth is also a magnet, which is how a compass works. If a compass always points south, inside the Earth, at the geographic North Pole, what's the magnet up there? Inside the Earth, at the geographic South Pole, that's inside the Earth. And it gets really confusing because if you take any navigation courses, they'll talk about magnetic north and they mean where the North Pole magnet is on the Earth, but it's actually a South Pole. Because the magnetic north/south pole isn't bang on our geographic North Pole. It's a few hundred miles. It drifts. Anyways, that's the inside of the Earth's magnet. So, north is by the North Pole. We refer to magnetic north as being by the North Pole, but it's actually a south magnetic pole underneath there. And that's why a compass needle points in the direction of magnetic fields, and that's why a compass needle points to geographic north. Example 1 says, draw in the magnetic field lines below. Well, I guess one line would go... Oh, hang on. We got two magnets here. 1 and 2. Okay. So, here, like poles... So we would probably have a North Pole start out that way and get repelled by this North Pole. Same with that one there. Same with that one there and that one there. We would have a magnetic field line go like that and like that. Probably like that and like that. And from way off the page coming in would be a magnetic field line. From way off the page coming in would be a magnetic field line. They basically would be moving, I'll come back in a second, in large loops like this. But the two North Poles would be repelling each other. And now, here's really why I'm glad I got to this topic. We're going to be having to draw three-dimensional pictures on flat two-dimensional paper. And so I'm going to show you the notation that we've come up with in physics. It's pretty easy to show something going up the page. You draw an arrow pointing up the page. It's pretty easy to show left and right. It's pretty easy to show down the page. How do you show into the page? Our symbol for into the page is going to be that. And that's meant to be the tail feathers of an arrow going into the page away from us. Although often we'll get lazy and we'll just put a big X. We won't draw the circle around it, especially if I'm typing. I can do a capital X really, really easy in a diagram, but to get that circle around it is a pain. So, and then to show something coming out of the page towards us, that's meant to be the tip of the arrow coming out of the page towards us. Although, again, often we won't even bother putting the circle around it because I can do periods when I'm typing pretty easily, and that's meant to be the tip of the arrow coming out of the page towards you. So now, Zach, we can start to do some three-dimensional diagrams. So let's talk about electromagnets. It turns out a wire that is carrying direct current also creates a magnetic field. This is why we said it's electromagnetism. You can't have one without the other. In other words, a compass will be deflected near a current-carrying wire. What direction? We're going to learn some right-hand rules. There are 3 of them. So staring at your phone right now would be prime foolishness, absolute prime foolishness. There are 3 of them. The first one is often called Ampere's rule. You point your thumb of your right hand in the direction of the current, the positive current, not the electrons. Your fingers curl in the direction of the magnetic field. So let me show you what I mean. Example 2 says, sketch the magnetic field. All of you lift your paper up vertically so that it's at the same angle as my screen. I'm going to stand up and be you. So all of us will have to put our pencil down if we're right-handed. This is one of the few advantages of being a lefty. I can draw while I'm doing my right-hand rule. We point our thumb in the direction of the current. What that means into the page? Our fingers curl in the direction of the magnetic field. Is the magnetic field around this wire clockwise or counterclockwise? It's clockwise. So if we were drawing magnetic field lines, the magnetic field lines would look like this. Arrow that way, arrow that way, arrow that way, arrow that way. And then there'd be a weaker magnetic field further out. But if I put a compass in this picture, to the left of the wire, the compass would point up. Above the wire, the compass would point right. To the right of the wire, the compass would point down. And underneath the wire, the compass would point left. So that's the current carrying wire magnetic field. That's the magnetic field for a single wire. Okay. Here I'm telling you the magnetic field is coming out of the page above the wire, going into the page beneath the wire. What direction must the current be flowing there then? To the left or to the right? So we're going to hold up our right hand. Oh, by the way, can I give you a little bit of advice? If you want to get these wrong, keep your hand in tight. You'll get it wrong. Get your hands out far away from your body. Okay? So the magnetic field is pointing towards us above the wire. Will it work if I hold my hand that way? Is that possible to have the magnetic field? Are my fingers pointing in the same direction as the magnetic field? I have to hold my hand this way. And your thumb tells you which way the current is going. Paige, is the current pointing to the left or to the right?
What? I'm lost. I'm not sure.
Okay. Did you hold your hand up and participate with me? You have to. No, I'm being dead serious. And I'll start calling people out if they don't, because you cannot learn this without participating. So let's walk through it again. Put your pencil down. Hold your right hand up. Okay. This looks like it's the wire because it's got a question mark next to it. It says, which way will the current flow? I guess what do these dots mean? This is an arrow coming out of the page towards us. That's the magnetic field. And going into the page. So the magnetic field is coming out of the page towards us and curling underneath the wire away from us. Which way is my thumb pointing? It's got to be that way. Okay? We're going to practice this. I have a whole bunch of practice. Oh, the right-hand rule works for positive charges. If you have electrons, you have 2 options. You can either use your left hand, which I find confusing, or I find it easier just to say, you know what? An electron moving left is the same as a proton moving which way? Right. An electron moving down the page is the same as a proton moving which way? An electron coming out of the page towards me is the same as a proton moving into the page towards me. I'd rather just make that flip, and then I can just get good with my right-hand rules. I've got 2 more. There's the first one. Okay? So here was a picture I found online. So if the current is flowing up, I would point my thumb in the direction of my right thumb in the direction of the current. My fingers curl in the direction of the magnetic field lines around the wire. So you imagine you're holding the wire in your fingers. That's rule number 1. Then we ask, what if you have more than one wire? What if you have several wires? We call this a solenoid. If we coil one piece of wire around and around and around in many, many loops, all in the same direction, we call the resulting coil of wires a solenoid. Let me give you an example of a solenoid. Will the magnetic field from a solenoid be? Here's right-hand rule number 2. Here's a typical solenoid. Oh, and we learned a long time ago that instead of just having the coil of wires around air, if you put a piece of iron in the middle, it dramatically increases the strength of the electromagnet, because the iron itself becomes a magnet. So we call this an electromagnet, and it has thousands, I should really say almost millions of uses. If you've ever seen, for example, videos of a big crane that can magnetically lift old cars, junk cars, and pick them up, that's an electromagnet. That's why that thing is always round shaped. It's a whole bunch of wires wrapped around and around and around. So, what's the rule for figuring out the magnetic field direction of a solenoid? This is right-hand rule number 2. You imagine that you're holding the solenoid in your hand, in your right hand. You curl your right fingers in the direction of the current through the wire, and your thumb points north. We're going to do one together. Example 4 says, what direction is the magnetic field below? But I deliberately didn't write in the solenoid because one of the things I'll show you is how you draw a solenoid. So we're going to draw a solenoid as follows. We're going to have a current coming in from the bottom. To draw a solenoid, go like that. And then to make it look three-dimensional-ish, what you do are really skinny capital S's like this. There's my solenoid. Or sometimes the capital S's will be reversed, facing the opposite direction. Okay? That gives you a kind of a 3D feel. And now I'm going to tell you which way the current is flowing. I haven't told you that. Suppose I told you the current was flowing this way. Okay? So imagine holding the solenoid in your hand. Everybody hold your right hand out like this. You can either hold it like this, or I guess you could hold it like this. But since it's a horizontal solenoid, your hand is horizontal. Curl the fingers of your right hand so that they follow the current. It looks like towards us, facing us, it's curling down. This, the way I'm holding my hand, doesn't work. My fingers are curling away. This, oh yeah, that works. Can you see my fingers are curling in the same direction of the current? My thumb points north. That's the North Pole. Yeah. That's the South Pole. The magnetic field lines would go like this then. Inside the solenoid, the magnetic field lines point to the right, but outside the solenoid, that's north, that's south. There's my magnet. We'll practice some more of these too. I'm going to scroll up. You can stay where you are. Looking at this one, it was tough to photocopy because it was originally a color picture. But if I zoom in, it looks like this is positive here. So the positive is going here. It vanishes behind. I think the current is going that way. So imagine holding that solenoid in your hand. Now you're going to hold your hand vertically, either this way or this way. Curl your fingers in the same direction as the current. That's wrong. It's got to be this way, yes? Your thumb points north. The North Pole, the bottom. So, I could get one. Yeah, I do. Good. We use solenoids in transformers, not the toys, but the actual electric devices, electric motors, generators, TVs, speakers, doorbells, fire alarm bells, cell phones, power door locks, etc., etc., etc. A friend of mine used to live in a very old building in downtown Vancouver. The building was built in 1930. And when I visited his building, I saw his fire alarm Okay? This is a solenoid, and all they've done, this is an electromagnet, this wire coming in, it's not direct current, it's alternating current. Being on your phone a second time is walking a path to disaster. Being on your phone a third time will be very, 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 very foolish. So stay off your phone. They've hooked this up to alternating current. So instead of the current flowing in one way, it's going this way, then this way, then this way. So very rapidly, this is going north-south, 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 north-south. This has a little magnet on the end of it, right there. And that magnet gets attracted, repelled, attracted, repelled, attracted, repelled, which makes this go ding, 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 and there's your bell sound. The ones you folks have in our modern schools, I think all they did is they clued in, why don't we put the bell around the solenoid so that all the mechanism is hidden so people can't vandalize it. I'm pretty sure that's how your phones are vibrating. There's a small solenoid in there and some kind of an electromagnet and some kind of a weight that's going back and forth. It might be a rotational thing as opposed to a vibration. I don't know. It used to be a solenoid. You're not old enough to remember. Phones used to actually ring with bells, and that bell was a solenoid. I have an old dial-up phone that's back there that I took apart, and sure enough, there's a couple of lovely solenoids in there. Probably, again, I don't know about cars in the last 10 years, but the original electric locks on cars, all it was an electromagnet pointed vertically, and when you turned it on one way, the North Pole was here, and that pulled the magnet down and pulled the lock down. When you flipped it, that reversed it, and that repelled the lock up. Modern locks now don't go up and down. They're hidden. The old locks, we used to be able to see them from the window that went up and down. So some technology has changed. I'm going to skip example 5. Going to do example 6, though. Which end will be north? Figure it out on your own. Don't write out your answer. Which end is north, A or B? B. This is the really tricky one. This is the one we'll try tomorrow. But first, can you scroll to example 11, please? Turn to example, scroll, do it. Turn to example 11. Do that one on your own. What's that little circle with a dot meant to illustrate? I guess it's telling me that the current is coming out of the page towards me. So use your right-hand rule for a current-carrying wire and circle whether you think the correct answer is A, B, C, or D. Example 11. What's the correct answer? A, B, C, or D. What's the correct answer? So we would point our right thumb in the direction of the current. I guess this is the wire coming out of the page towards me. What is it? Gotta be A. No, A. Not O. A. Okay. Number 12. Ignore this part for a second. We'll come to that. Tell me which side is north, X or Y. Use your right-hand rule on your own and label the diagram correctly. I find it easier to draw the current arrows on. Which side is north, X or Y? When I drew in, when I followed the current from positive, I said, okay, it's coming over that way. X is north. Yes, no, yes, no. You can ignore this part of things. I'm not going to get into that. There's more to it than that, but we're cutting corners. Can't do that one yet. Can't do that one yet. Can't do that one yet. Okay. No homework. Your homework is, I wanted to give you 15 minutes. I gave you 11 minutes. Sorry. You can work on circuitry. You can ask me questions. Make sure I show you my cool magnetic videos, but those are going to be tomorrow.